So there's quite a number of different redox reactions which we need to consider. So we've got our combination reactions, our decomposition reactions, single replacement or single displacement reactions, double replacement or double displacement reactions, combustion reactions, and disproportionation reactions. So you've probably come across most of these, if not all, throughout your chemistry journey so far. And so I would say that you'll have a general understanding of what these are, but probably not in the context of redox. So we're going to go on and talk about what these different types of reactions are and how they work. So our combination reactions, these are the most simple type of reaction which we consider. They're quite basic and typically don't require an extensive amount of balancing. And essentially they're where two different elements are going to be combined to then form one chemical compound. And so we can consider the combination of hydrogen and oxygen. So for example, where we've got 2H2 plus O2, and that's going to make 2H2O. So if we're to consider how we look at this in a redox context, we could say that we know that each hydrogen atom is going to have a charge of 0 because it's H2, it's solely made up of hydrogen, and so hence, because it's only made up of hydrogen, each hydrogen atom is going to have a charge of 0. We can then look at oxygen, which is the exact same concept, because it's oxygen gas, it's entirely made up of oxygen atoms only, and so hence each oxygen atom is going to only have an oxidation number of 0, and the entire molecule will also have an oxidation number of 0. So we can say that this is 0, this is 0, and then when we get to the final reaction, we can see that following our rules that we have, so rule number 5 is going to tell us that hydrogen is going to have an oxidation number of +1 per hydrogen atom. So because we've got two of them, it's going to be 2 times +1, which gives us +2. And then we know based on rule 6 that oxygen is going to have its oxidation number of -2. So we've got +2 and -2, and that gives us 0 overall. And so when we consider that, that tells us that water has an oxidation number of 0, oxygen has its oxidation number of -2, and hydrogen has its oxidation number of +1 per atom. And we can say that this is redox because hydrogen is going from 0 to +1, so it's losing 1 electron per hydrogen atom, whilst oxygen is going from 0 to -2, so it's gaining a electron per hydrogen, 2 electrons per hydrogen, per oxygen atom. So essentially the oxygen is receiving electrons from the hydrogen atoms. So when the hydrogen loses those 4 electrons, because we've got 2 times 2 is going to give us 4, it's going to lose 4 electrons and give those 4 to the 2 oxygen atoms, because 2 times the oxygens, and then those 4 electrons which are lost are lost from the hydrogen, resulting in the hydrogen being oxidized and the oxygen being reduced. And so if we consider that in terms of the oxidizing and reducing agents, we can say that hydrogen is the reducing agent, and oxygen is the oxidizing agent. Our next one we can look at is the opposite of that, so that's our decomposition reactions. So a decomposition reaction occurs when a chemical compound breaks down into each of its constituent elements. So we can see here we've got AB makes A plus B. So essentially they've just been separated down into their constituent parts, and typically these are just the opposite of your combination reactions. So often you can have a combination reaction that is reversible and can reverse back down into this. So if we're to consider, for example, the decomposition of water, it's basically just the opposite of what we just looked at before. So we can say we start off with H2O, and so we've got 2 H2O, and so we know that the hydrogen is going to be a +1 charge per hydrogen atom, and the oxygen is a -2 charge per oxygen atom. And we know that once we get to the H2 here, that's got a charge of 0, because that's following rule 1. It's only made up of one element type. And same with our oxygen, that's only made up of one element type. So when we're looking at hydrogen, hydrogen's going from +1 to 0. So it's gaining an electron per hydrogen atom. Whereas our oxygen is going from -2 per oxygen atom to 0 per oxygen atom. So we can say that the hydrogen, in going from +1 to 0, is gaining 1 electron per hydrogen atom, whilst the oxygen going from 0 to going from -2 to 0 is losing 2 electrons per hydrogen atom. So because of that, we can say if hydrogen is gaining electrons, we can say that hydrogen is being reduced, whilst the oxygen is losing electrons, we can say the oxygen is being oxidized. And so if the hydrogen is being reduced, that means that it is the oxidizing agent, because when it loses its electrons, it's donating them to, so when it gains those electrons, it's being donated them by the oxygen. So the oxygen is losing 2 electrons and hence is being oxidized, and so hence it is the reducing agent. It's causing the hydrogen to be reduced. So essentially the oxygen will lose 2 electrons and enable the hydrogen to be reduced by donating those 2 electrons. And the hydrogen will have, from the water, will have lost electrons, will have gained those electrons in order to enable the oxygen to then actually donate those across. The next reaction we're going to look at is a single displacement reaction. So a single displacement reaction involves the replacement of one element with another element within those products. So we could consider if we have A plus BC, we do a swap over and we end up with AB plus C. So a really good example that we've got here is we've got Cl2, so that's chlorine gas, plus 2 NaBr, so 2 sodium bromides, and then we've had a single displacement reaction which has resulted in the formation of 2 sodium chloride or NaCl molecules and bromine gas or Br2. And so we can say that this is a redox reaction because not only is this a single displacement reaction in which we can see that in this compound of NaBr we're swapping out chlorine for the bromine, but we've then also got that it's a redox reaction in that we can see the chlorine is starting off as a charge of 0 in total, so its oxidation number is going to be 0 based on rule number 1 because it's entirely made out of chlorine. Then we can see the sodium and the bromine. We can go on to our rule number 3, which tells us that sodium is going to have a +1 oxidation number because it is a group 1 metal, and we remember based on rule number 3, group 1 metals will have a oxidation number of +1. And then we've got bromine, and we know with bromine that fits into our rule number 7, which tells us that our group 17 elements are going to have a charge or an oxidation number of -1. So +1, -1, and yep, that's right, that gives us 0 in total, and this is an uncharged molecule, so that's correct. We can then see, so chlorine's going to go from 0, sodium is going to go from +1, and bromine is going to go from -1. We can then see in our next, in our products, that sodium, we've got sodium chloride. So following our rules again, we go to rule number 3, which tells us that sodium is going to have its charge of +1 because it's in group 1 of the periodic table and it's a group 1 metal. Then chlorine, going on to rule 7, we know that our group 17 elements are going to have a charge of -1. So we've got sodium is staying as +1, but chlorine is changing to -1. So chlorine is going from +1, 0 to -1. So chlorine goes from 0 to -1. So it's gaining 1 electron. Then we look at bromine, and bromine here is bromine gas. And so bromine gas is purely made up of just bromine. So we use rule number 1, which tells us that its oxidation number is going to be 0 for each bromine atom. So we can see that bromine is going from -1 to 0. So this is an interesting one in that the sodium is what we call a spectator ion. And so a spectator ion does not participate in the reaction as such. So it's there participating in the reaction itself, but not participating in the redox component of the reaction. So it's not actually changing its oxidation number, it's not donating or accepting electrons, it's just serving as an atom that can be bonded to enable the others to form new compounds with their charges. So we've got the chlorine going from 0 to -1, so it's gaining 1 electron, and so because it's gaining 1 electron, we can say that it is being reduced. And because it's being reduced, we can say that it is the oxidizing agent. When we look at bromine, bromine is going from -1 to 0. So each bromine atom is losing one electron because it's going from -1 to 0. And we're remembering that electrons have a negative charge. And so that means that because bromine is losing an electron, it is being oxidized, and hence it is the reducing agent. So bromine is essentially losing electrons and acting as a reducing agent by then donating those lost electrons to the chlorine so that the chlorine can be reduced. And then the chlorine is subsequently acting as an oxidizing agent to then gain those electrons which have been lost by the bromine. So next we're going to look at the double displacement reactions. So double displacement reactions are very similar to a single displacement reaction. However, instead of only one element being replaced, we've got two elements being replaced. So we've got AB plus CD makes AD plus CB. So we can see that there's this double switch over between these existing compounds and to then form these new compounds. So an example which we have here is we've got magnesium sulfate plus sodium bicarbonate makes magnesium bicarbonate and sodium sulfate. So in this particular reaction, we want to determine what our charges are that we're starting off with and what is changing, so we can determine what is being oxidized and what is being reduced. So when we look at magnesium, we look at magnesium sulfate to start off with, and we want to look into our rules. So our rules tell us that our oxygen is going to have a -2 charge, and each magnesium is going to have a +2 charge. But we also need to remember that we have 4 oxygens. So we can use Rule 6 for oxygen and Rule 7 for magnesium. However, we've got 4 oxygens, so we'll do -2 times by 4, and that gives us -8. -8 plus 2 from the magnesium is going to give us -6, which means that we want this to equal up to 0 as a whole because it is needs to fit in with rule number 2, that it is a neutral compound, so it needs to have a charge of 0. So it's got -6, so in order to go from -8 plus 2 gives us -6, in order to get to 0, we need to then have a charge or an oxidation number of +6 for the sulfur. So then we can get -8 plus 6 plus 2, and that will give us 0. The next one we want to look at is our sodium bicarbonate. So we start off with, we can look at Rule 3, and Rule 3 is going to tell us that the sodium is going to be, we know it's a group 1 metal, so it's going to have a charge of +1 per sodium atom. So that's +2 overall because we've got 2 of them. Then we've got oxygen. So we can go into Rule 6, which tells us we've got each oxygen is going to have its charge of -2. So we can do -2 times by 4. And so -2 times by 4 gives us-8. So -8 plus 2 gives us minus 6. And so now we need to fill in for the carbon. And so using rule number 2, we know that this entire compound does not have a charge on it, and it's neutral, so it's going to have an entire oxidation state of 0. So hence we need to get it to equal 0 with all those sums of the oxidation numbers. So this is minus 8, then plus 2 is going to give us minus 6, and then we've got 2 carbons. So we can't say that carbon is going to be plus 6 because there's 2 of them. We need to divide it between the 2 of them. So we do we need plus 6 in order to do that. So we do plus 6 divided by 2 is going to give us plus 3 per carbon atom. So if we've got 1 plus 1, plus 3 plus 3, minus 2 minus 2 minus 2 minus 2, that in total is going to give us 0. So now we need to look at what our products are to determine how these are changing. So if we look at our magnesium bicarbonate here, we can see that we've got magnesium. Following our rules, magnesium is going to be a plus 2 charge. Oxygen is each going to be a minus 2 charge. So we've got minus 8 plus 2 gives us minus 6. Each carbon is going to be, each carbon here is going to be plus 3 because we've got 2 of them. So nothing's changed there. The magnesium is going from positive 2 to positive 2. Our oxygen is going from minus 2 to minus 2. And our carbon is going from plus 3 to plus 3. So nothing's changed in that context there. So we can completely ignore that for the moment, and we'll look onto our sodium sulfate. And so with our sodium sulfate, we first of all want to go to rule 3. And so rule 3 tells us that the sodium each sodium has a charge of plus 1, and so that exists to be the same as previously. Each oxygen has its charge of minus 2, so we've got minus 2 times by 4 gives us minus 8, plus 2 gives us minus 6, and then the sulfate is going to be plus 6. And so that also remains the same as well. And so we can see it appears that we don't actually have a redox reaction occurring within this reaction. However, if we're to break it down and we're to look in the data booklet, we've got these charges which happen for the ions. And so although each individual element on its own is not changing its redox charge, there's actual redox changes in the sulfate ion and the bicarbonate ion, but not within the individual atoms themselves. But you don't need to worry about that too much in terms of your exams and this syllabus, but I just thought it's useful to point it out in order to show you that although this can appear that it's not redox, it is still considered a redox type reaction and still can be a redox reaction. The next one we're going to look at is our combustion reactions. So combustion reactions, they basically always involve oxygen in the form of oxygen gas, so O2, and they're basically pretty much all of the time are going to be an exothermic reaction. And they're going to follow this typical rule where they need to have some sort of hydrocarbon, so something that involves hydrogen and carbon bonded together, then reacting with oxygen, and this occurs under heat and will form pretty much all the time is going to form carbon dioxide and water as its products. So when you see something where its only products are carbon dioxide and water, and there's oxygen as one of the reactants, you can typically then assume that you've got a combustion reaction. And so, although I did say that typically a combustion reaction is going to involve a chemical that is oxidized by oxygen, many other chemicals can burn in different environments, that being like nitrogen gas, chlorine gas, fluorine gas, but typically it's going to be oxygen, and that's the one which you look at throughout grade 12 and unit 3 and 4. But just here's some examples just to show that it does in fact occur under other circumstances, so don't be surprised if someone does mention a combustion reaction which burns in a different condition. So for example, we've got 2Ti plus N2 can make 2TiN, so that's a combustion reaction that doesn't have that typical appearance of carbon dioxide plus water. And then similarly, we've got like 3 magnesium plus nitrogen makes magnesium nitride. So these reactions, you wouldn't be expected to know that they're a combustion reaction. You would be told that they're a combustion reaction if you were given those type of reactions. However, ones like these here, up the top, where you've got your typical hydrocarbon reacting with oxygen and then producing carbon dioxide and water, you would obviously then be expected to know those are a combustion reaction because they're following that typical combustion reaction type pattern and reaction pathway. Our final reaction that we're going to look at is called a disproportionation reaction. And so in these types of reactions, you've got a single substance that is being both oxidized and reduced at the same time. And so this is going to be like this example here where we've got 2A makes A, and then you've got plus a number and A minus a number. So it's basically like one compound splitting into 2 compounds, one of which has been oxidized and one of which has then been reduced. So in this example up the top here, that's saying where N is your number of electrons which has been transferred. And so these reactions have some practical application, such as when you have hydrogen peroxide, which gets poured over a cut in terms of this, for sterilization, and this performs a decomposition reaction. And so we've got oxygen which is present in all parts of the equation, and it's being both oxidized and being reduced. And so this is why you keep hydrogen peroxide in a dark bottle, because otherwise it will just spontaneously decompose under the presence of light. So when we're looking at this, we can see we've got 2 hydrogen peroxide, or 2H2O2, makes 2H2O, 2 water, plus oxygen gas, or O2. And so when we're breaking this down into its oxidation and reduction, we can see that we can actually identify here that we have some exceptions to some of our rules. So we know that in our rules, hydrogen is going to have a +1 charge, and oxygen is going to have a -2 charge. But if we were to follow that rule in this particular circumstance, we would actually find that having hydrogen with a +1 charge and having oxygen with its -2 charge would not add up appropriately. So if we were to do hydrogen with a +1 charge, we get +1 +1, so +1 by 2 will give us +2, and then we have got 2 oxygens, so we have -2 by 2, and so that will give us -4 +2, and that will give us -2 overall. And so we can't have -2 overall, because -2 overall would mean that this is not a neutral compound, and we do know that this is a neutral compound, so that would not be correct. So hence we've actually got to change the oxygen, because in peroxides, oxygen has a charge of -1. So in this circumstance, we can say we've got hydrogen is +2, each one being +1, and then the oxygen, each oxygen will be -1, so then overall 2 by -1 will give us -2, so we've got -2 plus 2 will give us 0 overall. Then when we look over here, we can see that hydrogen is going to stay the same at +1 because it is a spectator ion. But in water, we know that oxygen has its charge of -2, or its oxidation number of -2. So we can say that we've got -2 plus 2, that gives us 0 overall. So we can say that the hydrogen is acting as a spectator ion in this circumstance because it hasn't changed. It's just acting to be bonded to by the oxygen. But this oxygen atom has gone from a -1 charge to a -2 charge. And so because it's gone from a -1 charge to a -2 charge, we can say that it has actually then gained an electron per oxygen atom. Then when we look at O2 here, O2 follows rule 1, where we say that each oxygen atom is going to have a oxidation number of 0, and the entire compound is going to have an oxidation number of 0 because it's entirely made up of only one type of element. So in that case, we're going from -1 to 0, so that's a loss of 1 electron. So we can see that the hydrogen's not changing. The hydrogen is purely just acting as a spectator ion, but the oxygen is going in 2 different ways and is being both oxidized and reduced. So the oxygen here is going from -1 to -2, so it's being reduced, it's gaining an electron, whilst the oxygen to the oxygen gas is going from -1 to 0, which means it is going to then lose an electron per oxygen atom, and so hence it's being oxidized. So we've got half the oxygen in here acting as an oxidizing agent to then be reduced for the water, and half of it being acting as a reducing agent so it can then be oxidized for the oxygen gas.